Welcome to the video for C6.1.6 Extracting Metals. So before you start this lesson, you need to look over some material from previous lessons, otherwise this isn't going to make any sense. So the first lesson you need to look at, if you can't remember the material, is C4.1.6 Reactivity of Elements, which we've done recently. So in this we talked about metal displacement reactions, and we should remember from both the metal displacement reactions and the halogen displacement reactions that we've done, the displacement reaction is where a more reactive element displaces a less reactive element from its compound. So in the case of metals, a more reactive metal is going to displace a less reactive metal from its compound. So if you have the reaction M plus NX to give MX plus N, where M and N are both metals, and X is a non-metal, then that reaction is only going to work if the incoming metal N is more reactive than the one that's in the compound N. So if it's less reactive, that reaction is not going to work at all. So the reaction will only work if M is more reactive. And this is important in today's lesson. The other lesson that you might need to look back over is C3.3.1 redox reactions. And in this lesson, we learned the acronym OILRIG, which stands for oxidation is loss, reduction of gain. And in that case, we're talking about electrons. Now, for this lesson, it's more useful to talk about oxidation and reduction in terms of oxygen. So oxidation is loss of electrons, but it's also used as meaning the gain of oxygen. And whereas reduction is a gain of electrons, it's also a loss of oxygen. So if you can't remember those two and you need more clarification, then go back and use your textbook to just have a quick look over that. So our learning objectives for today are to describe how copper is extracted from ores, explain why some metals are extracted using carbon and others need to be extracted using electrolysis, and to be able to write balanced symbol equations to represent the extraction of copper from its ore. So you need to know the specific example of copper. So before we start, here's our definition. So the definition of an ore, and they quite often ask this in an exam question, is that it's a rock or mineral which contains enough metal to make it worth extracting the metal. So quite often people in exams write just about that it's a rock or mineral which contains metal. It's not just that it contains metal, it's that it contains enough metal so that there's a high enough percentage of the metal that it's worth extracting it. If there's only a small percentage of the metal in the rock or mineral, then it costs too much to extract it and it's not used. So we're just quickly going to revise the reactivity series. So you've seen something like this before where they're listed from reactivity. So in this case, we've got the most reactive at the top and the least reactive at the bottom. And you can see all of those are metals apart from carbon and hydrogen, which are in red. And we don't need to worry about hydrogen, that's there for when we do about electrolysis, which we've already done. But for today, we're worried about the metals and we're worried about carbon. So when we've got that reactivity series, we can use our reactivity series to predict whether a displacement reaction is going to happen. And if you've got a more reactive element, it's going to displace a less reactive metal from a compound. So an example there is if you had potassium, which is at the top of the reactivity series, and copper, which is quite low down, then potassium would react with a copper compound, in this case to give KCl, and the copper would end up by itself. But this only works if the metal that's by itself is more reactive than the metal that's in the compound. So if it was the other way around and we had potassium chloride and we added some copper to it, nothing's going to happen because the copper is not reactive. So why is this important? So when we're talking about extracting ores, as we've said, a more reactive element is going to displace a less reactive element. We can use this to extract metal from its ores. So carbon's quite cheap, it's very abundant. So we can use carbon to extract some ores, some metals from their ores. But we can only do this if carbon's more reactive than the metal that we want to extract. So if you look at the reactivity series that's written there, anything that's lower in the reactivity series than carbon, so zinc, iron, tin, lead, copper, silver, gold, platinum, anything that's low in the reactivity series can be extracted using carbon because the carbon will come along and it can displace it from its compound. Anything that's more reactive than carbon, so on there we've got potassium, sodium, calcium, magnesium, aluminium, they can't be extracted using this method because they're more reactive than carbon. So the carbon's not going to be able to steal away the other element from the ore because it's not reactive enough. So if it's more, those elements that are more reactive than carbon, you need to use electrolysis. You could actually use electrolysis for any of those elements, but electrolysis is a lot more expensive due to the cost of the energy, especially the electricity that you need to do that process. So if we can use carbon, we will use carbon because it's cheaper. So when we do our extraction using carbon, as we said, we only use this for metals that are less reactive than carbon, and the general Worth equation could be something like this. So metal oxide plus carbon to give metal plus carbon dioxide. So we need to think of this in terms of being a redox reaction, so in terms of reduction and oxidation happening. So in terms of oxygen, it's easier to look at this in terms of oxygen. So when we talk about oxidation and reduction in terms of oxygen, so oxidation, or when something is oxidized is when it gains oxygen, and when it's reduced or reduction, it's losing oxygen. So in this example, the metal is losing oxygen, so it's being reduced, and the carbon's being oxidized, gaining oxygen. If we look at this in terms of electron, then the metal is being reduced because it's gaining electrons, and the carbon is being oxidized because it's losing electrons. But it's easier to see in this equation in terms of oxygen rather than electrons. We'd have to look at specific examples to look at the electrons. So you need to know the specific equations for extracting copper. So when we extract copper from its ore, some of the ores are the oxides themselves, so it's easy just to stick the carbon in. We can do the reduction reaction straight away. But in the case of copper, it's more usual that the ore that's used for extraction is copper sulfide. So you can't react that directly with carbon. So instead, you react the copper sulfide with oxygen to give copper oxide and sulfur dioxide. And then that copper oxide that you've produced in that stage one can then be reacted with the carbon to give you the copper, which is what you want to do, and carbon dioxide. So you need to learn both the word equations for that process and the balanced equations, simple equations. If you look at these simple equations for stage two, hopefully you can see that that's a redox reaction. So we've already talked about it in terms of oxygen. So the copper's losing oxygen, so it's being reduced. If you wrote out if you look at the copper on the left-hand side of that, and you wrote out what the charges on the copper and the oxygen are, so the oxygen would have a charge of 2 minus, and the copper would have a charge of 2 plus. Whereas on the right-hand side, the copper is just by itself, so it's not got any charge. So it's going from a 2 plus charge to no charge. So it's gaining electrons to go from 2 plus to just copper on the right-hand side. So it would be copper 2 plus 2 electrons to give copper. So you can see from that that it is reduction. Okay, that's the end of the lesson. Thank you for listening.